Assalamu alaikum dear students, in connection with the second lecture on the fundamentals of organic chemistry. We are going to discuss about what's conjugation, what's hyperconjugation, resonance, and rules of. So briefly, conjugation, as we studied in the earlier lecture, the previous one, we said electrons which are fixed between two nuclei only are called localized electrons, since the bonding is called localized bonding. But if the electrons are shared between more than two nuclei, such electrons are said to be delocalized, and the system containing delocalized electrons are called conjugated. So when we mean by a conjugated system is that any system that has alternate single multiple bonds, that may be single alternate double single bond, double single double bond, triple single triple bond, as you can see on the slides. Such systems are called conjugated system, right? So similarly, systems in which a multiple bond is in conjugation with a p orbital, that means that there is a multiple bond separated by a single bond, and to that single bond we have a p orbital, then such systems are also called conjugated system. So you can see that from structure number 1, structure number 2, structure number 3, there are examples of multiple bond in conjugation with multiple bonds, while the structure number 4 presents a double bond which is in conjugation with the p orbital. So all of these are type of conjugated systems, right? So whenever there is a system which is in conjugation, then it is compulsory that electrons are delocalized. Electrons cannot remain localized in a system that is conjugated. So next important thing that we are now going to study is the resonance and the role. Right, so firstly consider these structures. We have, so we have 4 carbons and there's a chlorine. Then we have 6-membered ring with a double bond, and then we have a 3-membered ring with oxygen, and attached to is 2-carbon chain. So there are the formulas, these are the structural formulas which represent different organic compounds. In all of these cases, these structures are sufficient to give information about the reactivity and properties, I mean the bond length, bond angle of these all compounds. However, there are certain cases in which we cannot give a single structure, We cannot give a single structure and explain all of its bond lengths, bond angles, etc. For example, consider example of 1,3-butadiene, right? So 1,3-butadiene is a conjugated system, it's a conjugated structure. It has double bond alternating with another double bond. The double bond separated by a single bond, then a double bond, right? So if we consider the bond lengths, right, so we say that a double bond is shorter than a single bond, right? So the bond length for a double bond is 1.34 Armstrong, right? But the bond length for a single bond is 1.54 Armstrong, because single bond is longer. However, when we consider the bond length of butadiene, all of these bond lengths, the bond length for single bond as well as double bonds, is equal and is intermediate between the bond lengths of a single and a double bond, right? So it means that there is some problem. These findings suggest that a single structure cannot explain all the properties of this molecule, right? So in order to solve this issue, what we do is that we use 2 different structures here, structure number 1 and structure number 2, and we said that both of these structures together explain the properties of this molecule, which is butadiene. So both of these structures are not real, but they are contributing towards an original structure, right? The original structure had the properties of both of these forms, but neither of these structures is the original structure. So butadiene and all other conjugated compounds cannot be represented by one structure. They have to be represented by more than one structures. A single structure is not sufficient enough to explain all the properties of an original compound. So you have to draw more than one structure for a real structure, and each of these structures has certain attribute of original structure, and yet neither of these structures is real. So such structures which are used to describe the original structure is called the canonical forms or the contributing structures, whereas the original structure is said to be resonance hybrid of the canonical forms. So one thing is important, always remember, canonical forms are imaginary, they are not real. Resonance hybrid is a real molecule, but its structure cannot be drawn. The real structures of the resonance hybrid is said to be the weighted average of all the contributing structures. Right? What do you mean by weighted average? That the canonical form that resembles most with the original structure has greater average. Right, so canonical forms are imaginary, they're not real. The real structure is of resonance hybrid, but structure cannot be drawn. Right, the real structure for resonance hybrid is said to be a weighted average of all the contributing structures. Representation of a real structure as a weighted average of contributing structures is called resonance. In simplest words, you can say that representation of the representation of a real structure by means of more than one structure is called resonance. Right? So if you can represent a single structure and explain all properties for that structure, for that compound, this is not resonance. Resonance only means that there is a structure for which you cannot draw a single structure, and you have to make use of more than one structures for explaining an original structure, but neither of right. However, you can cause substitution on the benzene ring. You can replace one of the hydrogens with anything, right? So you cannot undergo addition reaction on benzene ring under normal conditions. This extraordinary stability of benzene is called aromaticity. Okay, so now we have a summary for resonance. Any hypothetical structure with different arrangement of electrons but with identical positions of atoms is called resonance structure, the canonical form, or the contributing structures. So what do you mean by hypothetical? Hypothetical structure is any structure that's imaginary, that's not real. So different imaginary structures or different hypothetical structures which have different arrangement of electrons but the position of atoms is same, these structures are called canonical forms, resonance structure, or the contributing structure. Right? They are real, and the actual structure is considered as a hybrid of all of these valid resonance structures. Right? So resonance structures or the contributing structures can only exist on paper, they're not real. Another thing, that the resonance hybrid has the lowest energy of all the contributing structures. It means that resonance hybrid is actually the most stable form. Right? So all canonical forms, all resonance structures have higher energy because they are not real, while the resonance hybrid is the species which is real and has the lowest energy. Right. So rules of resonance. Right. So firstly, the contributing structures, again, which are imaginary, differ only in the position of pi electrons, but the position of atoms should remain same. Right. Second rule for resonance is that all contributing structures must be proper Lewis structures. What we mean by that, the valences must be satisfied in each and every structure. For example, carbon can only form 4 bonds. You cannot form 5 bonds for carbon, right? And if the valency is not satisfied, the canonical form will not be the true canonical form. For example, consider the structure 1 and 2. So nitrogen is forming 4 bonds here, and nitrogen is positively charged. So this structure is right. But the next structure, in which nitrogen is forming 5 bonds, is not possible, because nitrogen can never form 5 bonds. Okay, next is the resonance hybrid is the actual structure and more stable than any of the contributing structures. The resonance process is represented by double-headed arrow. It must not be confused with this arrow. So this double-headed arrow means that the structures of both ends are imaginary, while the second arrow represents a state of equilibrium. right? So whenever a system has resonance, it has extraordinary stability, right? And the reactivity for that system decreases. Benzene is stable because of resonance. The sixth rule for resonance is that equivalent structures have equal contribution. For example, so equivalent structures have equal contributions. For example, two calculus structures for benzene, they are equivalent. They are similar, so they contribute to equal extent. While the D-word structures, these are equivalent, so they have equal contributions. Right? Structures with charge separation have lower contribution than structures without charge. So we have two structures. One has no charge, and the other has charge. Then the structure with no charge will be more stable than the structure with charges. Right? The next rule is that if you have contributing structures and the structure in which there is a negative charge or negative atom, negative charge and electronegative atom, that will be more stable than a negative charge and an electropositive atom or less electronegative atom. For example, consider these structures. So in this case, we have a negative charge on carbon and a positive charge on chlorine. So chlorine is more electronegative. So having a positive charge and electronegative atom makes the system unstable. The structure number 2 will have lower contribution. That means this contributing structure will have low stability and lower contribution, while the structure number one, it has no charge. Secondly, the structure number 2 with positive charge and electronegative atom is destabilizing the structure number 2. Right? So structure number 1 will have more contribution than structure. So after the rules of resonance, we will consider rules for writing canonical forms. So whenever you have to write a canonical form, there are certain rules. Number 1, whenever you write a canonical form, always keep in mind that the Lewis structures must be a bona fide Lewis structure. Means the valency of all atoms must be satisfied. So nitrogen cannot form 5 bonds, but nitrogen with 4 bonds with positive charge on nitrogen, that's right. So structure number 1 is a bona fide Lewis structure, while structure number 2 is not a bona fide Lewis structure, because nitrogen here is forming 5 bonds, which is not possible. Second, the position of atomic nuclei or the atoms in all canonical forms must be same. There should be no change in position. For example, consider structure number 1. Here we have negative charge on oxygen, which is singly bonded. Here we have negative charge on oxygen. So we have just shifted the pi electrons. We have not changed the position of atoms. The oxygen remains at its position. Right? So these are the right canonical forms. But consider this one. Here in the structure number 3, we have a CH3 at one end, and in the next structure we have a CH2, and one of the hydrogen from CH3 has shifted on oxygen. So here we have changed the position of atom. So since we have changed the position of atom, this is not the right canonical form. Right? So structure 3 and 4. For summary, we consider the resonance is nothing but just a way to represent a structure. It cannot be represented by a single structure. So resonance is a way to represent a structure which cannot be represented by a single structure. So whenever we make use of 2 or more structures, then this is called resonance, right? So resonance always occurs when a system is conjugated, right? So you should know in your mind what do you mean by conjugation. When there is alternation in double, single, double bond, triple, single, double bond, or any multiple bond alternating with single bond, or any multiple bond that is in conjugation with the p orbital, then we have resonance. Whenever there is resonance, system is conjugated. Whenever system is conjugated, we cannot represent the structure by a single one. We have to make use of 2 or more than 2 structures to explain an original structure which cannot be represented. Why it cannot be represented? Because if we represent that structure, then in that case the rules of valency will be violated. So this is all about resonance. And is about hyperconjugation, right? So previously we saw the resonance involves the delocalization of pi electrons. We only changed the position of pi electrons, but the sigma bonds was remaining the same. Sigma bonds remain untouched. However, in some cases the sigma bond is also delocalized, right? So whenever a single bond and an adjacent pi bond get involved in resonance, such type of delocalization is called hyperconjugation. For example, consider a structure. So we have here carbon-carbon single bond, right? And this carbon-carbon single bond is attached to a double bond, right? So whenever this hydrogen, you can say this blue bond between carbon and hydrogen, so what is being done, that this bond is shifting towards carbon-carbon single bond, and the hydrogen is becoming free here, and this pi bond is shifting a negative charge. So what we have done is that we have delocalized, we have shifted the electrons of a sigma bond, which is called delocalization, and we have shifted the position of a double bond as well, right? So this delocalization of sigma and pi electrons is called hyperconjugation, and hyperconjugation involves interaction with sigma bond in a pi network, right? You can say, we can write this way, or we can write also in another way if we have shifted this other hydrogen, right? So we have different forms representing this structure. So these are also, since resins, this is also delocalization. So in delocalization we cannot represent a single structure to explain the structure of a real molecule. So this is also resonance, but since instead of pi electrons, sigma electrons also delocalized, such type of conjugation is called hyperconjugation, right? So in case of hyperconjugation, what you should keep in mind, that whenever there is a carbon possessing at least one hydrogen, and this carbon is attached to a carbon bearing an unhybridized p orbital, right? So unhybridized p orbital means that carbon has a positive charge, because positive charge is always in a p orbital, or the carbon is unsaturated, part of unsaturated system. That means carbon is double bonded or carbon has a triple bond. Then such a structure can only be presented by more than one structure. You should keep in mind, whenever there is a double bond or there is a triple bond, and to this double or triple bond we have a sigma bond attached, then this sigma bond will be involved in resonance, right? If they have all of the sigma bonds, then there is no hyperconjugation. But whenever there is a sigma bond directly attached to a double or triple bond, then in such cases hyperconjugation will exist, and you cannot write just one structure for such a compound. So the canonical forms result from the overlap of the sigma bond of CH and the pi bond of p orbital for the, right? So just to explain that, consider this one. So we have carbon that's singly bonded, and we have this carbon that's the positive charge, right? The positive charge is in this weakened 2p orbital of the carbon. So what happens is that this carbon, this sp3 carbon, sp3 orbital of the carbon, is forming initially a sigma bond, head on head overlap with this hydrogen, that's shown by this blue region, right? So this sp3 bond, sp3 orbital of the carbon, overlaps with this weakened 2p orbital, leaving the hydrogen without any bond, right? So this bond between hydrogen and carbon does not exist anymore, because this carbon is forming a bond with this carbon by overlap of sp3 and p overlap, right? So the carbon forms a double bond with the carbon, and the hydrogen becomes free, right? The electrons with sigma bond between carbon and hydrogen are involved in delocalization. In the structure to the right, you can say here, there is no bond between carbon and hydrogen. So hydrogen will be positive charge, indicating that electrons are not present with this hydrogen, and the bond that was previously between the carbon and hydrogen exists no more. Therefore, hyperconjugation is also called no bond resonance. Right? The important thing is that it doesn't indicate that hydrogen is lost, but there is some degree of ionic character, and because that ionic character, the hydrogen is still showing attraction with the carbon, but there is no covalent bond between carbon and hydrogen in this case. So this hyperconjugation is also called no bond resonance, because in one of the canonical forms there is no bond between carbon and hydrogen, right? So again we have structure like this one. Okay. Hyperconjugation explains the stability of a carbocation. Right, the cation is any species that has positive charge, and if the positive charge on carbon, then species is called carbocation. Right, so carbocations are electron deficient; they have positive charge. Right, say this positive charge is residing in the p orbital of sp2 hybridized carbon. Right, so here we have positively charged carbon, and you can imagine that this positive charge of the carbon is residing in the p orbital of this carbon. Right, so we have a p orbital on this carbon, and next to it is a sigma bond. So the sigma bond between carbon and hydrogen will break, resulting in formation of carbon-carbon double bond, and the hydrogen becomes free. Right, you can see that positive charge on carbon has now shifted on the hydrogen. So in this way, we have stabilized the positive charge. We have ended the positive charge on this carbon. So carbon has no positive charge now. The carbon is not deficient, and the deficiency has been shifted on hydrogen. In this way, we can stabilize the positive charge. Right, we have diffused the positive charge. So how many hydrogens are there that can diffuse a positive charge increases the stability. For example, in this specific case, we have 3 hydrogens that are attached with this carbon, and all of these hydrogens can stabilize this positive charge on the carbon. Alright, so we say that we have 3 canonical forms. In each of these, different hydrogens is detached and stabilize the carbocation. So these 3 hydrogens help in diffusing the positive charge. Alright, so if more than 1 alkyl groups are attached to the carbon, the more the number of alpha hydrogens and the more possibility of hyperconjugation. For example, in case we have 3 alkyl groups, 3 methyl groups attached to carbon, right? So all of these 3 hydrogens will contribute and help in diffusing the charge on carbon. So we have 9 hydrogens can stabilize this carbocation. In case we have 2 methyl group attached, so these 2 methyl groups with 6 hydrogens can stabilize this positive charge. So we have 6 hyperconjugable hydrogens, and in case of this structure with only 1 methyl, we have 3 hyperconjugable protons that can stabilize this positive charge. But in case of methyl, we don't have any hydrogen that can stabilize this positive charge. So we can say that we have 3 alkyl groups attached, such carbocation will have greater stability. With 2 methyl groups attached, we will have lesser stability. With 1 methyl group attached, that will still have lesser stability, and with the methyl carbocation, it will have the least stability. Alright, stability is in terms of hyperconjugation. And so just like carbocation, we can also predict the stability of alkyl radical. So what we mean by radical? Radical means any species that has unpaired of electrons. So just like a positive charge remains in a p orbital, the radical also resides in a p orbital of the carbon. Right, so in this case we have carbon with an unpaired electron that's shown at the dot here, and this carbon is attached a carbon-carbon single bond, and we have 3 hydrogens attached with this carbon. So all of these hydrogens can stabilize this radical. How can it stabilize radical? Just imagine that this hydrogen, okay, that breaks the bond with the carbon, and we have a carbon-carbon double bond here, and the hydrogen gets free. So radical that was previously on this carbon is now on this hydrogen. So hydrogen has stabilized this carbon by taking the unpaired electron on itself. Similarly, in the other structure, we have another hydrogen that has taken up the unpaired electron, and the carbon has become stabilized. So we have 3 different resonance structures. We have 3 contributing structures that are helping in stabilizing the radical. Okay, so next hyperconjugation can also explain the stability of the alkenes. For example, consider the alkene here. You can say there's a carbon-carbon double bond, and the carbon-carbon double bond is formed by parallel overlap of the unhybrid p orbital. So we have sp2 hybridization here, and these unhybrid p orbital, they are forming the carbon-carbon double bond. It's forming a pi bond. And now we have a methyl group here, it's carbon, that's forming a sigma bond with hydrogen here. So there's a sigma bond between hydrogen and carbon, and this sigma bond between carbon and then there's a double bond between carbon double bond. The sigma bond next to double bond always show hyperconjugation. It will happen that p orbital of this double bond will overlap with the sp3 orbital of this methyl group, so hydrogen will gain free again, and we have a negative charge on this carbon, right? So we have delocalized by electrons, we have delocalized sigma electrons as well, and again we have no hydrogen, no bond between carbon and hydrogen here, so this is called no bond resonance. So we can say that this sigma bond is causing delocalization of the electrons. The delocalization means this is resonance, and resonance increases. Two different methyl groups, both will cause the stability of the. Now bond lengths. Hyperconjugation causes shortening of sigma bond. So sigma bond has ideal bond length of 1.5 for Armstrong knot, and in case if we have methyl acetylene, means we have carbon-carbon triple bond, and to this is attached carbon-carbon sigma bond. The sigma bond has the actual bond length of 1.54, but in this specific case, the sigma bond has a bond length of 1.46 Armstrong knot, and this is very strange, right? Why is it strange? Because sigma bond is expected to be 1.54 Armstrong knot, but in this structure it has reduced, it has shortened. So we have to explain why it's shortened, because of hyperconjugation. You can see here, the hydrogen has shifted its electronic density between carbon-carbon double bond, right? In this triple bond, it has broken one of its pi bond here. So we have two carbon-carbon double bonds between carbon and carbon, right? So 1.46 Armstrong knot is bond length for carbon-carbon double bond, which is satisfied that why this bond has shortened. So hyperconjugation causes shortening